Hello dear students, welcome back to our YouTube channel. As you know that we are studying about the inverse Laplace transform. In previous lecture we have seen the first shifting theorem and let's take a brief review of previous lecture. We have the statement of first shifting theorem is if inverse Laplace transform of f of s is equals to f of t, then prove that inverse Laplace transform of f of s minus a is equals to e raised to a t f of t. Since we know that the definition of inverse Laplace transform of f of t is equals to integration from 0 to infinity e raised to minus st f of t dt, and this expression is equals to f of s. We are converting after taking Laplace transform of f of t, we will get the capital F of s, where s is operator. Since we have f of s is equals to integration from 0 to infinity e raised to minus st f of t dt, we replace s by s minus a. So f of s minus a is equals to integration from 0 to infinity, s is replaced by s minus a. So wherever s is there, we have to replace by s minus a. After replacing s by s minus a, we will get integration from 0 to infinity e raised to minus st plus at f of t dt. By using law of indices, we can write it as integration from 0 to infinity e raised to at into e raised to minus st f of t dt, and it is the definition of Laplace transform. So we can write it as f of s minus a is equals to Laplace transform of e raised to at f of t, and shifting Laplace transform to left hand side or applying inverse Laplace transform to both sides, we will get inverse Laplace transform of f of s minus a is equals to e raised to at f of t. Correct. Similarly, if we replace the operator s by s plus a, we will get e raised to minus at f of t. Correct. Now we will see the second shifting theorem. Since second shifting theorem is also based on first shifting theorem, that's why we have reviewed all previous lecture. Now the second shifting theorem, and it is stated as if inverse Laplace transform of f of s is equals to f of t, if inverse Laplace transform of f of s is equals to f of t, then inverse Laplace transform of e raised to minus as f of s is equals to gt, where gt is equals to f of t minus a and 0 whenever t is greater than a and whenever t is less than a. Correct? The function gt is given as f of t minus a whenever t is greater than a and 0 whenever t is less than a. We have to prove inverse Laplace transform of e raised to minus as f of s is equals to gt. Now, as we have seen in previous theorem, first shifting theorem, we have just applied definition of Laplace transform to f of t. So similarly, we will apply Laplace transform, definition of Laplace transform of f of t. So we will get Laplace transform of f of t is equals to f of s is equals to integration from 0 to infinity e raised to minus st f of t dt. Correct. Now we have the function g of t, so we have to replace f of t by gt, and it will give us g of s is equals to integration from 0 to infinity e raised to minus st g of t dt. But the function g of t is defined in two different intervals. One is from 0 to a and another from a to infinity. So Laplace transform of g of t will use us integration from 0 to a g of t e raised to minus st g of t dt plus a to infinity e raised to minus st g of t dt. Correct? Now put the values of g of t with respect to the interval. We will get integration from 0 to a e raised to minus st, and value of gt is equal to 0 dt, and a to infinity e raised to minus st, and it is f of t minus a. F of t minus a. Correct? Now put t minus a is equals to u, then we will get t is equals to a plus u. Correct? And whenever t is equals to a, this implies that u is equals to 0. Just replace t by a, we will get a minus a equals to u, that is 0. And when t is equals to infinity, because we have the limit points a and infinity. So whenever t is infinity, infinity minus a finite number, so we will get again infinity. Correct? And for dt, if you differentiate with respect to x, we will get dt is equals to dq. Correct? So the integration becomes 0 to infinity e raised to minus s, t will give us a plus u, f of t minus a becomes f of u, and dt becomes dq. Correct? Now law of indices, using law of indices we will get e raised to minus sa into e raised to minus su f of u d, and since e raised to minus su f of u du is a Laplace transform, so we can write it as Laplace transform of, and it is free from u, so we can take it outside as minus a, and it is Laplace transform of f of u. Correct? And we can write it as f of s also, and we have the result we have g of s is equals to correct. Now g of s is equals to this, or we can write it as e raised to minus as f of s, and it is g of s or Laplace transform of gt. Now gt becomes inverse Laplace transform of e raised to minus as f of s, and it is the required result for our theorem. So we have completed our second shifting theorem, in which the statement is as follows: if inverse Laplace transform of f of s is equals to f of t, then prove that inverse Laplace transform of e raised to minus as f of s is equals to gt, where g of t is equals to f of t minus a whenever t is greater than a, and 0 whenever t is less than a. By using the definition of Laplace transform, that Laplace transform of t is equals to f of s, which is equals to integration of 0 to infinity e raised to minus st f of t dt, we are finding the Laplace transform of g of t. So we have replaced f of t by g of t. So Laplace transform of g of t is equals to g of s is equals to integration from 0 to infinity e raised to minus st g of t dt. Correct. Now using the definition, we will value of g of t in two different intervals are different. So we have split our integration from 0 to infinity to 0 to a and a to infinity. We know that the integration, we know that the rule integration a to b f dx is equals to a to c f dx plus c to b f dx, where a is less than c is less than b. Correct. So we can split such in such manner to this integration. So we have split our integration a to infinity to 0 to a and a to infinity. Now we have just put the value of gt particular in that interval. So we have from 0 to a, we have the value 0, that's why we have put here 0, and we have a to infinity f of t minus a, so we have put a to infinity f of t minus a. Now replacing t minus a by u, so t becomes a plus u, and whenever the value of integration or limit of integration is a to infinity, so whenever t is a, u becomes 0, and whenever t is infinity, u become infinity, and putting these limits of u, integration becomes 0 to infinity e raised to minus s a plus u f of u du. Correct. Now just using law of indices, integration from 0 to infinity e raised to minus s a into e raised to minus s u f of u du. Now applying inverse Laplace transform, and we will get the result for second shifting theorem. In next lecture, we will try to find some more theorem. We will try to prove some more theorems which is based upon inverse Laplace transform. Especially this theorem satisfy a Heaviside function if f of t minus a is equals to 1. It becomes Heaviside function. Means up to 0 to a, we will get value on x-axis 0, and after a, it will use us value a up to infinity 1, and 1 up to infinity. So we will discuss this also in next lecture. Till then, thank you. Bye.